We're going to talk a little bit about what it means for a signal to be even or odd. We say that a signal x of t is even if x of t is equal to x of minus t. Well, essentially what this means is this, is that the signal x of t is symmetric about the y-axis. Well, the reason that is true is because if you take the signal x of t, then x of negative t is just the signal x of t flipped about the y-axis. If x of t has to be equal to x of negative t, then what this means is that if I take a signal and then I flip it about the y-axis, it has to be exactly the same as the signal. So for example, if I have a signal which looks like this, then either you can mathematically verify that if I pick any value of t here and then I observe what the value of x of t is at this point, it's exactly the same value taken by x of t at t is equal to negative t. Okay, so that's the mathematical way to think about an even signal. Or pictorially, you can see that if I take this signal, the triangular signal that I have here, and then I flip this about the y-axis, I would get exactly the same signal back. Okay, so that's what we call as an even signal. And what is an odd signal? Well, an odd signal is one for which x of t is the negative of x of minus t. Or equivalently, you can say that x of negative t is negative of x of t. Well, what does that mean? That means that if I start with a signal, say it looks like this. And then if I flipped this signal about the y-axis, I would get a signal which looks like this. Now you can see that the dotted signal is actually the negative of the original signal that we started with. In this case, we say that the signal x of t is an odd signal. Okay. So one of the interesting things about even and odd signals is the fact that any signal x of t can be written as the sum of an even part and an odd part, or the sum of an even signal and an odd signal. So any x of t can be written as x sub e of t, which we are going to call as the even part of the signal x of t, and x o of t, which we can call as the odd part of x of t. Okay, it turns out any signal x of t can be written this way. I should be more clear. Any real signal x of t can be written this way. Okay, we'll talk a little bit about complex signals a bit later. But for now, let's assume that all these signals x of t are real. Well, how can we see this? Well, we can see this by explicitly giving a decomposition for x of t. So what I could do is this. I can start with x of t and write x of t as follows. I can write x of t as half x of t plus half x of t. But I could add and subtract half of x of negative t. Oops, I need to subtract this here. Okay. Now if I do this, I could group these two terms together and then these two terms together, and I will show you that this is an even part, or this signal is even, and then this signal is odd. And therefore we can write x of t as the sum of an even part and an odd part. Okay, it's easy to see that the first part is even and the second part is odd. In fact, I would urge you to stop the video at this point and then just convince yourself that the first part is in fact even and the second part is in fact odd. Um, yeah, it's probably a good idea to stop the video now. Okay, so if you're resuming the video, then let's see why this part is even. Well, if I define xe of t as half x of t plus x of minus t, now you can see that xe of negative t. What is xe of negative t? Well, it's whatever I obtained by replacing t by minus t in this expression, right? And what will I get if I replace t by minus t? Well, I'm going to get half of x of minus t plus x of t. Okay, which is in fact the same as what we started with. So what that really means is that the signal xe of t is such that xe of t is the same as xe of negative t, which implies that this is even. And the same idea can be used to show that the other part is odd. And you can see this by defining xo of t to be equal to half x of t minus x of minus t, and this implies that xo of minus t is half of x of minus t minus x of t, which is in fact equal to the negative of xo of t. Hence xo of t is odd. So here's an example. Say we want to find the even and odd parts of the signal x of t that's shown in the figure. Alright, so how can we do this? Well, let's first recall that the even part of this signal x of t is given by half of x of t plus x of minus t, and the odd part is given by half of x of t minus x of minus t. So it's clear that we have to first find the signal x of minus t. So what is the signal x of minus t? Well, x of minus t is just a flip of this signal about the y-axis. So x of minus t is a signal which looks like this. So now all we have to do to find the even part is to add these two signals and then take half of that. And to find the odd part, we subtract x of negative t from x of t. So when we do that, well, here's what I'm going to get for the even part and the odd part. Let me try to do this here. So the even part is going to look like this. So it has a height of 1/2, and so this is xe of t. Now the odd part is going to look like this. So what's going to happen is x of t minus x of minus t. So this part is going to get flipped about the x-axis, and so I'm going to get something like this. Remember, the height is 1/2. Okay, so this is the odd part of the signal x of t. Okay. Let's work out one more example. Um, say we want to find the even and odd parts of so here I wouldn't advise you to actually try to draw the picture, so on and so forth. It's easier to just manipulate the expressions directly, because x of minus t is going to be cosine of negative t plus sine of negative t plus cosine of negative t times sine of negative t. But we know that cosine of negative t is the same as cosine t, and sine of negative t is negative sine t, and so this term, the last term, is going to become cosine t times sine t. And now I need to add these two signals and take half of that to get the even part. So the even part is going to be, when I add them up, I'm going to get 2 times cosine t, but half of that is simply going to be cosine t. And the odd part, I have to take the difference of x of t and x of negative t and then take half of that. Or you can say, well, I know that my x of t can be written as an even part and an odd part, and I already know that this is the even part, so this has to be the odd part. And in fact, that's what will happen when you subtract this expression, or rather this expression, from this expression. So the answer is that's the odd part. Okay. Now, the definition of even and odd signals for real discrete time signals is identical to that for continuous time signals. We'll just replace x of t by x of n. So the even part, or rather a signal x of n, is even if x of n is equal to x of negative n. Okay. And x of n is odd if x of n is equal to negative x of negative n.